We're surrounded by energy all the time. It's in the light we see, the sounds we hear, but have you ever stopped to think about how that energy actually gets from point A to point B? Well, today, we're diving deep into the world of waves, the invisible, secret movers that basically power our entire universe.
Okay, so let's start with a little riddle. Think about it. You've got a musical instrument, a kitchen appliance, and this massive force of nature. On the surface, they have absolutely nothing to do with each other. But they all share one single powerful secret. Any guesses?
That's it, waves. It sounds simple, but it's huge. The sound from that guitar, the heat in that microwave, the signal to your phone, the light from the sun, it's all waves. So today, we're going to break down exactly what they are and how they pull it all off.
Okay, so first things first, we need to get a handle on the absolute core idea of what a wave even is. And it's a concept that's actually really simple, but also kind of profound. And this right here is the key, the whole ballgame. Imagine you toss a pebble into a pond. You see that ripple, that wave move across the water, right? But the water itself, it just bobs up and down. A duck floating on the surface wouldn't travel with the ripple. It would just go up and then down. The wave is just the energy traveling, not the stuff it's traveling through. And that difference, it's everything.
Now, not all waves are created equal. You've got two main types. First, there are mechanical waves. Think of sound or our pond ripple. These guys need a substance to travel through, what we call a medium. They need particles to bump into each other. No air, no sound. But then you have electromagnetic waves. These are the weird ones. Light, radio waves, microwaves, they don't need anything to travel through. They can cruise right through the total, complete emptiness of space.
And on top of that, they move in different ways. A transverse wave is what you'd see if you took a long rope and shook one end up and down. The wave zips forward, but the rope itself is just moving up and down, at a right angle to the wave's direction. A longitudinal wave is more like a slinky. If you push one end, you see a compression move down the slinky. The coils are moving back and forth in the same direction the wave is traveling. That's exactly how sound works.
All right, now that we know the basic types, let's learn the lingo. Let's really dissect a wave and look at all its different parts. It's like learning the anatomy of this incredible energy mover. So any wave you can think of can be described by these four things. Amplitude is basically its power or intensity. You can just think of it as the wave's height. Wavelength is the literal distance from one peak to the very next peak. Frequency is how often those peaks are passing by, how many of them go past a certain point every second. And here's the cool part. They all connect to give us the wave's speed. The math is simple, but it tells us that how fast a wave travels depends on its frequency and its wavelength.
So we know waves can travel, but what happens when they actually run into something? Well, this is where their behavior gets really interesting. Let's see how waves bounce, bend, and interact with the world around them. First up, you've got reflection. This one is super intuitive. It's just a bounce. A wave hits a surface and bam, it bounces off. The one simple rule to remember is that the angle it comes in at is the exact same angle it leaves at. And here's what's important. When a wave reflects, nothing about the wave itself changes. Not its speed, not its frequency, not its wavelength. It's just a change in direction. So, where do you see this in real life? Well, everywhere. We use this simple bounce for some incredible technology. Sonar maps the entire ocean floor by timing how long it takes for sound waves to bounce back. A satellite dish? That's just a big curved reflector designed to bounce all the incoming radio waves into one single point. And medical ultrasounds create a picture of what's inside your body just by analyzing how sound waves bounce off different tissues. Okay, next up is refraction. And if reflection is a bounce, then refraction is a bend. This happens whenever a wave crosses from one type of material into another, which causes its speed to change. You've definitely seen this before. If you put a straw in a glass of water, it looks like it's bent at the water's surface. That's not an illusion. The light waves are literally slowing down and bending as they go from the air into the water.
And this is a perfect way to see it in action with water waves. So that normal line is just an imaginary line. We draw at a right angle to the boundary between deep and shallow water. As ocean waves come toward the beach, they move from deep water into shallower water, and they start to slow down. That change in speed makes them bend toward that normal line. And that is exactly why waves almost always look like they're rolling in parallel to the beach, even if they were coming from a totally different direction way out at sea. It's all refraction.
And finally, we've got diffraction. This is the amazing ability of waves to spread out and bend around corners.
This is the reason you can hear someone talking in the next room even when you can't see them. Their sound waves are diffracting, spreading out as they pass through the doorway. And this effect is way more obvious for waves with longer wavelengths, which is why sound and radio waves seem to bend around corners so much better than light does.
Okay, so we've seen what one wave does on its own, but what happens when two waves run into each other, when they meet in the same place at the same time? The result is called interference, and it's all governed by one simple, really elegant rule.
That rule is called the principle of superposition. Now, that sounds kind of fancy, but the idea is actually super simple. You just add them up. That's it. Wherever the peak of one wave meets the peak of another, you add their heights together. Wherever a peak meets a valley, or a trough, you subtract them.
And this leads to two totally opposite results. When the waves are in sync with their peaks lining up, they build on each other, like they're giving each other a high five. That's constructive interference. It makes the wave bigger, the sound louder, the light brighter. But if they're perfectly out of sync, where the peak of one wave lines up exactly with the valley of another, they completely annihilate each other. That's destructive interference, and it can literally create silence out of sound or darkness out of light. And we have figured out how to use this power of cancellation in some amazing ways. Noise-canceling headphones are pure genius. They don't just block sound. They have tiny microphones that listen to the noise around you, and then they instantly create a new sound wave that is the mirror opposite. They blast it into your ear, and poof, destructive interference cancels out the noise. It's like magic, but it's just physics. All right, for our last section, let's zoom all the way out and look at one whole family of waves that is absolutely critical to our modern world, the electromagnetic spectrum. So every single wave in this family shares one unbelievable property. In a vacuum, in the emptiness of space, they all travel at this exact speed, 300 million meters per second, the speed of light. It is the undisputed, unbreakable speed limit of the entire universe. Nothing goes faster. Think of the whole spectrum as one big, continuous family. The only thing that separates a radio wave from an X-ray is its frequency, and therefore its energy. They all travel at light speed, but as you go up this list, the waves get shorter, more frantic, and packed with way more energy. Higher frequency equals more power. And we use every single part of this invisible spectrum. You've got long, low-energy radio waves for broadcasting TV and radio. Microwaves power our cell phones and cook our food. X-rays let us see inside our bodies. And even the most powerful, highest-energy gamma rays are used in medicine to fight cancer. These are the invisible waves that literally run the modern world. So here's the big takeaway. Whether it's a mechanical wave you can see in a pond or an invisible electromagnetic wave from a distant star, they are all governed by the same set of fundamental rules. Reflection, refraction, interference. It's a universal language that energy uses to move through the cosmos. And that really brings us to the final thought. We've managed to master this science, to send messages across the planet in an instant, and to peer inside the human body without a single cut. But science is never done. So the real question is, what's next? What new discoveries about waves are waiting just around the corner? And what incredible technologies will they unlock for us? Thanks for tuning in.